This lesson is for section 10.6. Today we're going to introduce to you a completely new concept, and that's the polar coordinate system. We have a lot of objectives for today. I just tried to simplify them as much as possible. But what we're going to do is graph polar coordinates, and we're going to change from polar to rectangular form and vice versa. We're also going to find the distance between two polar coordinates, and we're going to write the equation of a circle in polar form. So up until this point in your math careers, you guys have dealt exclusively with the Cartesian coordinate system. We call that the rectangular coordinate system also, or sometimes the XY coordinate system. But basically, not everything is graphed easily in that Cartesian coordinate system. So now we introduce to you a new coordinate system called the polar coordinate system. So a coordinate system, all it does is describes the location of a point in space. Okay, what you're used to is the Cartesian system, which says how you're supposed to move horizontally and vertically to get to a specific coordinate. So let's say we have a point here, P. Well, we define P as being a certain number of units away in the x direction, so horizontally in the x direction, and y units vertically, and we call that point xy. Now in the polar system, though, we define that point P a little bit differently. So here, instead of going moving horizontally and vertically, we actually describe the distance straight from the origin to that coordinate. Okay, and we call that distance r. And we also determine the angle that that segment makes with the positive x-axis. So we would define this point here by the distance it is away from the origin and the angle measure that is formed when you create that segment. So to describe that polar system a bit more, I'm going to go through some formal definitions with you. Similar to the Cartesian system, we're going to start with a fixed point in the plane, which I'm going to label O, but we can call that the origin, like in the Cartesian plane, but a lot of times it's called the pole instead. So it's either the pole or the origin. And then it's customary to draw a ray from that pole in the positive x direction. Okay, we call that the polar axis. Now, like I said, each point P in the plane can be described by coordinates P as r comma theta, where r is the distance from O to P. So if I draw a point P here, r is going to be the distance between O and P, and theta is the angle measure between the polar axis and the segment OP. So between the axis and the segment OP. Now, if theta is positive, we measure counterclockwise, just like we do in the unit circle. If theta is negative, then we measure in the clockwise direction. So we'd go this direction here if theta was negative. Now, if r is negative, something different happens. So let's say we have some point P where r is negative, so r is less than 0. Well, we define P as being r units from the pole. This really should say the absolute value of r because we're just taking the distance away from the pole, but it's in the opposite direction of theta. So we have our pole here and our polar axis, and we're supposed to represent the point r comma theta when r is negative, where it's r units from the pole in the opposite direction of theta. So I'm going to draw in theta real quick. So let's just say I have theta here. Okay, I want to be in the opposite direction of theta. Well, the opposite direction of theta is this direction here. So the opposite here. Now, it's supposed to be r units away, so I could just make any segment length here and call this r. But this would be the coordinate r comma theta if r is negative. All right, so let's get some practice now graphing in the polar coordinate system. Now, as you can see, our Cartesian or the rectangular coordinate system is a little bit different than the polar system. In the polar system, we have a series of concentric circles centered at the pole or the origin here. And each of them represent the same distance away from that origin. So here this segment is 1 unit away, then 2 units away, 3 units away, 4 units away, and 5 units away. Now if we want to plot these points here, the first one is defined as 1 comma 3 pi over 4. Remember, this is the distance, and here is your angle measure formed with the positive x-axis. So if I want to be 1 unit away from the pole at an angle of 3 pi over 4 from the positive x-axis, I'm going to find that angle measure here. So there's that 3 pi over 4, okay? And I want to be 1 unit away, which means I'd be right here, okay? So this distance here represents 1 unit from your pole. So there's the point A. Now the second point B is listed with a negative value for your angle measure. So we have a negative angle measure. Remember, this time you're going to go clockwise from the positive x-axis here. So from your polar axis, we want to go negative pi over 6. which means we're going to be at the same value here as 11 pi over 6. And I want to be 3 units away this time, so that means I'm here on that third rung. So there's point B. Now C is 3 comma 3 pi, so I want to be 3 units away at an angle measure of 3 pi. So if I start at the polar axis and I go counterclockwise, this is going to be 2 pi, and then I have to go around and stop here. So this is the coordinate C, 3 comma 3 pi. Now for D, we have a negative value here for the R. So remember, distance isn't negative, but what this is saying is you need to go at the opposite direction of the given angle. So here's pi over 4. Okay, I want to be in the opposite direction of pi over 4, which means I'm over here at 5 pi over 4. So I'm going to go 4 units away, and that places me here for point D. So you might have already caught on to the fact that any polar coordinate can actually be represented in an infinite number of ways. So for example, that point D here, that was negative 4 pi over 4, but it's also the same as 5 pi over 4, right? It's the exact same angle measure as 5 pi over 4. So it's different than the Cartesian system, because in our Cartesian system, when we define a point, x, y, as let's say 3, 5, this is a unique point. You can't describe that in any other way. You can't say anything other than 3 units to the right and 5 units up to describe that particular point. Whereas in the polar system, we have an infinite number of ways to represent any coordinate. So we can represent a coordinate in either of these two ways. And I'm not going to break down the form, but those are the general forms of how you can represent a coordinate. We're just going to practice it and actually list a couple different polar coordinates for a point. So we're going to start with a point 2 pi over 3. Which means we're right here for point P, 2 pi over 3. Now I want to list 2 points where R is positive, so R is greater than 0, and where R is negative. So if we list our 2 coordinates here, for R being positive, then we want positive 2. And then I can just add pi over 3 to pi over, 2 pi to pi over 3 to get the exact same coordinate, because if I just go around one more time, I end right back up at P. So I would end up with 7 pi over 3. Okay, that's the same. Or if I wanted to go negative here, if I go in the negative direction, I can make a negative angle measure here, and that would be negative 5 pi over 3. Okay, so that's just 2 of the ones that I chose to do. There's obviously an infinite number of ways to write that same coordinate. You could just continue to add 2 pi to theta. Now, if R is negative, so if you have a negative 2, then I can also list this an infinite number of ways. So if I use the coordinate negative 2, 4 pi over 3, that would also describe the location for point P, because remember, when you have a negative value here, you're going to go to 4 pi over 3. So I'm here, but I'm in the opposite direction of 4 pi over 3, which means then I'm going 2 units away from the origin, which places me right at P. If I want to use a negative angle measure, I could say that negative 2 pi over 3 is also the same coordinate for P, because if I go negative 2 pi over 3, that places me here, and then I'm going to go in the opposite direction, okay, 2 units away, and again, I'm right back at P. So again, there's an infinite number of ways to do to list a polar coordinate. So oftentimes we need to actually know simultaneously a polar coordinate and its rectangular form. So here in this diagram, you can see the 2 systems overlapping. So we've got some point, P, defined as xy, and r theta. Now, just by using Pythagorean theorem and right triangle trig, I can come up with a few different relationships. So based off of this fact that this is a right triangle, I know that x squared plus y squared should equal r squared. I also know that the cosine of theta is equal to x over r. The sine of theta is equal to y over r, and the tangent of theta is equal to y over x. So these are some straight relationships that I get just based off of this diagram. Now what this is helpful for is converting between polar and rectangular coordinates, because here if I solve for x, I have x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Now when I'm given a rectangular point and I want to convert to polar coordinate form, that means that I want to go from xy to r theta. So those are the 2 pieces of information that I need to have. Now in this case, I'm given the coordinates negative 1, 1. Remember, negative 1, 1 is in the second quadrant. Okay, so that's where our coordinate definitely is, because remember, there's an infinite number of ways to list a polar coordinate, but we want to make sure that that coordinate would represent something in the second quadrant. So I have an x, a y, and I want to know r. Well, if you look at our first equation, which was given from the Pythagorean theorem, this relates x, y, and r together. So we've got negative 1 squared plus 1 squared should equal r squared. In other words, r is equal to the square root, and this is going to be positive or negative, square root of 1 squared plus 1 is 2, so square root 2. Okay, now I need to find theta next, right, in order to get that coordinate. Now for theta, I could use either of these two examples, but then I'd have to plug in r and I'd have to do a little bit more work. Instead, I'm just going to use the tangent of theta is equal to y over x, because again, it relates theta and y and x. This is exactly the information that I have. So the tangent of theta should equal 1 over negative 1, or tangent of theta equals negative 1. Now that happens at two different locations on our unit circle. So theta could equal 3 pi over 4, but it could also equal 7 pi over 4. Now we got to remember though that our coordinate, this xy coordinate, lies in the second quadrant, so I can list this two different ways. I can say positive root 2, 3 pi over 4, because that would give me something in the second quadrant, but I could also list that as negative root 2, 7 pi over 4, because that would give me that would take me in the opposite direction. I could also list negative root 2 negative pi over 4, and this would probably be something that you're most comfortable with if you're using your calculator, because remember your calculator, when you do the inverse tangent of negative 1, it's going to spit out an angle measure that's between negative pi over 2 and pi over 2, so it won't actually tell you 7 pi over 4, and it won't tell you 3 pi over 4, it'll give you that negative pi over 4. So that's the value that it's going to give you. So you might be more comfortable with this one, but there's obviously a lot of different ways that I can represent that same coordinate, but here are just a few. Now in the second example, I have an x, y, 0, 2, so this time again I'm going to set up x squared plus y squared equals r squared. So I continue to relate the variables that I'm given. Since I have an x, I have a y, I want to find r, that's the equation I'm going to use. So I have 4 equals r squared, so r is equal to positive or negative 2. Now this time when I solve for theta, I have the tangent of theta is equal to y over x, so 2 over 0. Now this is undefined. So I need to think, when is the tangent of theta going to be undefined? Well, theta then will be pi over 2, or at 3 pi over 2 it's undefined, and also at negative pi over 2, right? Okay, so if we were going to list the coordinates here, remember that your coordinate 0, 2 is right here on the y-axis. So if I want to define this using polar coordinates, I have r, so let's use positive 2 first, 2 pi over 2. Okay, that describes that location here in terms of its polar coordinate. I could also describe that though as negative 2, negative pi over 2, because we're going to go in the opposite direction of negative pi over 2. So here's where negative pi over 2 is opposite direction, places me up here, 2 units away. Now I could also list that as negative 2, 3 pi over 2 also. Negative 2, 3 pi over 2. Any of these all work. Again, there's an infinite number, but if I go negative 2, 3 pi over 2, 3 pi over 2 is here. Go in the opposite direction, and you're back here up at 2. Okay, so I think that's a little bit trickier. When you're given polar coordinates, finding the rectangular coordinates, I think, is a little bit more straightforward. Okay, in example 2a, I'm given the polar coordinates 5, 2 pi over 3. Remember, that represents r and theta. And I want to know what the xy coordinate is. Now, instead of using x squared plus y squared equals r squared, and the tangent of theta equals y over x, I'm going to use the two formulas that give me x and y in terms of r and theta, because I know both r and theta. So I know that x is equal to r times the cosine of theta, and I know that y is equal to r times the sine of theta. So to find x, I'm going to take 5 times the cosine of 2 pi over 3. And to find y, I'll take 5 times the sine of 2 pi over 3. So I have to evaluate here. So I have 5 times the cosine of 2 pi over 3 is going to be negative 1/2. And I have 5 times the sine of 2 pi over 3, which is going to be positive root 3 over 2. So 5 times root 3 over 2. This gives me the unique coordinate. The x value is negative 5/2. And the y value is 5 root 3 over 2. So the reason why I'm saying it's a unique coordinate is because we can only represent this rectangular coordinate in one way. That's why I think it's a little bit more straightforward than converting from rectangular to polar coordinate form, because you can use multiple representations of the same point, whereas in rectangular form, this is the only point that represents this in the Cartesian system. Okay, I will let you guys try B on your own. Just because there's a radical here does not make it any different than a. So remember, you're using r times the cosine of theta to find x, and for y, you'll use r times the sine of theta, okay? And then now we'll just move on to converting rectangular equations to polar form. So sometimes it's to our advantage to convert a rectangular equation to its polar form just because it's easier to graph, and vice versa. So that's what we're going to practice now, and this is a skill that's related to exactly what you're doing when you're converting points. So we've got the equation x squared equals 4y. Okay? Our goal is to only see x and y here in terms of r and theta. I don't want to see any more x's, I don't want to see any more y's, all I want to see are r's and thetas. So what I'm going to do is use a substitution here. I know that x squared is equal to r times the cosine of theta squared, and I know that y is equal to r times the sine of theta. So I'm just using that conversion, right? And then from here I'm just going to simplify a little bit. So this is going to give me r squared times the cosine of theta squared equaling 4 times r sine theta. It's customary to try to isolate r. So let's say I divided by r over the cosine of theta. Cosine squared theta, sorry. Well, over here, those r's are going to cancel, so I'm left with r equaling 4 times the sine of theta over cosine squared theta, which your book will probably simplify even further from here. So if you want to check that in the back of the book, you'd end up with 4 times the tangent of theta times the secant of theta, because you've got sine theta over cosine theta times another 1 over cosine theta. So this would be this equation here, the rectangular equation, in its polar form. All right, in example 4, I'm going to use some substitutions here so that I can express x and y in terms of r and theta. So I have 4 times r times the cosine of theta plus 7 times r times the sine of theta minus 2 equaling 0. All right, now, like I said, it's customary to try to get r alone. So if I want to isolate r, I can move over the 2 first. Okay, so let's make that equals 2. Then I'm going to factor out the r. If I factor out the r, I'm left with 4 times the cosine of theta plus 7 times the sine of theta. And then I can isolate r all by itself here if I divide out that 4 cosine theta plus the 7 times the sine of theta. So now I have r isolated, so r is equal to 2 over 4 times the cosine of theta plus 7 times the sine of theta. So this is this rectangular equation here in its equivalent polar form. Okay, next up is number 5, and in this case we want to convert this rectangular equation into polar form, and I can make substitutions here for x and y, but instead in this problem I want you to recognize patterns, okay? When you see x squared plus y squared, remember that's just equivalent to r squared, so rather than making substitutions separately for x and y, just go straight to x squared plus y squared equals r squared. Now I have r squared minus 8 times y is equal to r times the sine of theta equals 0. Now in this case I can factor out the r here, so I have r times r minus 8 times the sine of theta equals 0. Now I know it's kind of weird for you to divide by r on both sides, but r is definitely not equal to 0, okay? Otherwise, then this point is just the origin. So if r is not equal to 0, I can divide by it, and I have r minus 8 times the sine of theta equaling 0. And in other words, r is equal to 8 times the sine of theta. So this is the polar form for this particular equation. Now, converting a polar equation to its rectangular form is a bit trickier than when you go from rectangular form to polar form. We can't just make a direct substitution. A lot of times we have to put a little bit more thought in how we are going to manipulate the equation. So in these problems, I try to give you a little range. We start with some easier ones, and then we're going to work our way to some where we have to use identities. Now, after we find the rectangular form of the equation, I want to also determine the graph of that equation, okay, if it's possible. So let's start with number 6 here. We have r equals 5 times the secant of theta. Now this is the same as 5 over the cosine of theta. And right away I recognize I have an r and I have a cosine theta. If I can get them together, that would be a good thing for me because then I can make a substitution. So what I'm going to do here is multiply by the cosine of theta on both sides. Now I have r cosine theta equaling 5. And then I can make a substitution here. I know that r cosine theta is x, so I have x equals 5. So in this case, in its rectangular form, this is just the equation of a vertical line. X equals 5. Now in example 7, I see that I have r and I have sine theta. So, hopefully you're thinking in terms of making that a y, but the fact that they're not together means that you can't just make that direct substitution. So instead I'm going to manipulate this equation. It would be very helpful for me if I did have an r on that side of the equation, because then I can make that y. But if I want to multiply by r on one side, I need to make sure I multiply by r on both sides of the equation. So I'm going to do that, and I create an equivalent equation here. R squared is equal to 2 times r times the sine of theta. Now, whenever you convert from polar to rectangular form, your goal is to no longer see theta or r. So we want to see only in terms of x and y. Well, on the left-hand side, that's equivalent to x squared plus y squared. And on the right-hand side, obviously r sine theta is what we were going for here. We end up with 2y. Now, in this form, this is definitely in rectangular form here. It's not quite as easy to see maybe what the graph looks like of this equation. So I'm going to subtract that 2y over. And then at this point, we're going to use an Algebra 2 scale that we kind of worked on at the beginning of the year. So it's been a while since we've used this, but hopefully it'll come back to you really quick. We're going to complete the square here. Now, if I cut negative 2y in half and I square that number, so negative 2 divided by 2 is going to give me negative 1, then I will square negative 1 to complete the square. So I end up with a positive 1 after I square negative 1. Now, whenever you complete the square, you have to balance both sides of your equation. So I'm going to add 1 to the other side. And now I'm looking at the equation, x squared plus y minus 1 squared, equaling 1. So I just took this and I factored it into y minus 1 squared. So I just completed the square here. And now it looks like I have the equation of a circle with a center at 0, 1 and a radius of 1. So the graph here, let's make that the center here, 0, 1, would look like that. Now example 8 is pretty similar to number 7 because I see that cosine theta and the r here, but they're not together. So in order to try to introduce another r on the right hand side here, I'm going to multiply by r on both sides of the equation. So I end up with r squared equaling 2r plus 2r times the cosine of theta. Now I can make some easy direct substitutions here. This is going to give me x squared plus y squared equaling 2r plus 2x. Now, in this case, I still have that remaining r, okay? And to get rid of that, it's going to require a little bit more work. So now I'm going to subtract that 2x over, okay? So I'm isolating here the 2r. Now, if I try to multiply by r on both sides so that I create 2r squared here, the problem is that on this side, I'm going to end up with a bunch of r's, and I don't want to do that. So instead, to create r squared on the right-hand side here, all I'd have to do is square the right-hand side. Now obviously we can't do that on only one side of the equation, so I'm going to square both sides. Now here I'm not going to bother multiplying out all those terms. I'm just going to leave it in terms of x squared plus y squared minus 2x, the quantity squared here. But on the right-hand side I'll write that as 4r squared. Now at this point I can make a substitution in here. So I have x squared plus y squared minus 2x, the quantity squared, equaling 4 times x squared plus y squared. So if I simplify here, I could, if I wanted to, multiply out all of these terms, but I don't want to do that with you guys because I think it's a waste of time. And this is just a really ugly form, okay? So sometimes writing something in its rectangular form makes the graph really easy to look at. Like when you saw this here, it was just the graph of a line, and here, the graph of a circle. In this example, though, clearly, this is not easy to see what that graph is going to look like, and its polar form is actually the easier graph. So that's just kind of showing you an example of one where it doesn't make sense really to convert to its rectangular form. Now in number 9, you have to recognize here that rewriting the sine of theta minus pi over 4 is going to be your best shot at trying to eliminate r and sine theta. So what I have to do here is use my angle addition formula. Remember, you can rewrite the sine of theta minus pi over 4 as sine, cosine, cosine, sine. So we're going to take the sine of theta times the cosine of pi over 4 minus the cosine of theta times the sine of pi over 4. And then from here I can evaluate because the cosine of pi over 4 and the sine of pi over 4 are actual values here. Those are real numbers. So I have r equals, this is going to give me positive root 2 over 2 times the sine of theta minus, the sine of pi over 4 is also root 2 over 2. So I have minus root 2 over 2 times the cosine of theta. Now at this point I can multiply by r because if I multiply both sides of the equation by r, now I have r squared equaling root 2 over 2 times r times the sine of theta minus root 2 over 2 r times the cosine of theta. And from here I can make those substitutions. that are necessary to eliminate the r and the thetas. So I have x squared plus y squared equaling root 2 over 2y minus root 2 over 2x. Now in this case, I could complete the square and move those all over to the other side, but it's going to get pretty ugly here, so I'm just going to stop since this is already in rectangular form. Okay, now the last portion of our lesson, we're going to talk about the polar distance formula. So if you want to find the distance between two polar coordinates, you have to use a different distance formula, which is given right here. Okay. Now it looks really intimidating, but really it's just an application of the law of cosines. So here in the diagram, I think it's a little bit easier to understand what I mean. We've got 2 points, B and C, and we want to find the distance between B and C. So the polar coordinates of B are given by r1, theta 1. So this segment length here from A to B is r1. Here we have theta. That's the angle measure. Theta 1 is the angle measure formed between the positive x-axis and r1. Now the other point, C, is given by r2, which means that this length, AC, is r2. And here we've got our angle measure written as theta 2. Okay. Now we want to find the distance between those 2 points. So that would be represented by segment D here. Now to find that length, well, all I really did was create a triangle. So now I can use the law of cosines. Remember, the law of cosines says that this distance squared is equal to the sum of the 2 sides squared. So we've got the length here squared plus the other length squared minus 2 times the product of the 2 lengths, so r1 and r2, times the cosine of the angle here. Now this angle is measured as, or is written as theta 3. Now to find this angle, all you have to do is take the angle measures that you're given, so you have theta 2 and theta 1, and subtract. Now in this case I have theta 1 listed and then minus theta 2. It really doesn't matter which one you take, because whether this angle is positive or negative, remember the cosine of theta is equal to the cosine of negative theta, so it really doesn't matter which one you subtract. But that's your distance formula, okay? So now we can apply that here when we want to find the distance from these 2 polar coordinates. So just to keep this short, I'm going to actually set this up and then I'll talk through how we evaluate it. Alright, so there's the setup here to find the distance between those 2 polar coordinates. Now, if you were doing this without a calculator, it wouldn't be helpful actually to simplify pi over 6 minus pi over 4, because we don't know the value of pi over 12, but we can use an identity here, our angle addition identity, and rewrite cosine of pi over 6 minus pi over 4 in terms of, you know, cosine, cosine, change sign, sine. So in that case, it's not helpful to write this as negative pi over 2. However, I'm just going to assume that you would be able to use a calculator here. So if we wanted to give my exact answer, it would be the square root of 13 plus 6 times the cosine of negative pi over 12. You could drop that negative sign also, because cosine of negative pi over 12 is the same as the cosine of pi over 12. But anyhow, that is your exact answer. So if you wanted to find the approximate, you would obviously just type that into your calculator. And finally, as a direct result of the polar distance formula, we can actually arrive at an equation that describes any circle in polar form. So let's say we have a circle with a center at r sub 0, theta sub 0. Okay. Now, the distance between any point on that circle and that center, let's call that distance A. Well, that point, an arbitrary point, is just defined as r comma theta. So if we found the distance between any points here, we would end up with this particular equation. So this is just denoting that A is the center, A is the radius, and the center is at r sub 0, theta sub 0. So in example 11, where they ask us to find the equation of a circle with radius 1 and center at 2 pi over 6, I find it helpful just to make sure I'm writing in the correct information here. I'm going to label A as 1, and if my center is at 2 pi over 6, then that center is r sub 0, theta sub 0. All right, now from here I can just plug it right into that formula. I have 1 squared is equal to r squared plus r sub 0 squared is going to be 4 minus 2 times the product of r and r sub 0. So r sub 0 is another 2 here, times the cosine of theta minus pi over 6. And from here, if I just simplify a little bit, I have 1 equals r squared plus 4 minus 4r times the cosine of theta minus pi over 6. So this is the polar form for an equation of a circle with a radius of 1 and center at 2 pi over 6. Okay, and finally, we are to our last problem of the lesson. Here we're supposed to find the equation of a circle with radius 5 and whose center is at 0, 0. This is actually not accurate though, because that looks like x, y Cartesian coordinates. And here, if I were to write the pole in polar form, that center at the origin, or the pole, okay, should be given by coordinates 0, theta, because if the distance between the origin and the pole is 0, then we don't really create an angle. You can't define the angle, so we just call it theta. So that's more accurate way of writing this. So I could have said radius of 5 and the center at the origin or at the pole, or the center at 0 theta. All right, anyhow. Now this problem is on here to highlight the fact that you have a special case of the circle equation when you have a center at the origin. Okay, if our center is at the origin, then that means r sub 0 is 0. And in your circle equation here, if r sub 0 is 0, then that term drops. And this entire expression here also becomes 0 because we're multiplying by 0 in there. So if that whole entire term drops, so for any circle with a center at the origin, the only terms that are left are a squared equals r squared. So we have a squared equals r squared, or equivalently, a equals r. Now in this case, a is 5, right? The radius is 5, so we have r equals 5. This is the equation of a circle in polar form with a radius of 5 and a center at the origin. So that is equivalent to its rectangular form, x squared plus y squared equals 25. This is just a little bit easier to write. All right, that is the end of the lesson. Nice job. See you guys tomorrow.